Chapter 14: Antennas and Propagation. Antenna propagation. Radio wave. A radio signal is called an electromagnetic wave because it is made up of both electric and magnetic fields. Magnetic field. A magnetic field is an invisible force field created by a magnet. An antenna is a type of electromagnetic. A magnetic field is generated around a conductor when current flows through it. The strength of magnetic field H produced by a wire antenna is expressed by H equals 1/2 pi d, where I is current and d is distance from wire. The SI unit for magnetic field is ampere turns per meter. Electric field. Electric field is also an invisible force produced by presence of potential difference between two conductors. The strength of an electric field E is expressed by E equals 1/4 pi E d squared, where Q charge between 2 points. E is the permittivity and D is distance between conductors. Permittivity. Permittivity is a dielectric constant of material between the two conductors. Dielectric is usually air or free space, which has an E value approximately 8.85 times 10 raised to negative 12, where ER is the dielectric constant of the medium. Magnetic and electric field in transition line. Any given time, the wires have opposite polarities. During one half of the cycle, the AC input, one wire is positive and the other is negative. Antenna operation. Antenna acts as the interface between a transmitter or receiver and free space. It either radiates or senses an electromagnetic field. The nature of antenna. If a parallel wire transmission line is left open, the electric and magnetic field escape from end of the line and radiate into space. This radiation, however, is inefficient and unstable and reliable transmission or reception. Impedance of space or wave impedance. The ratio of the electric field strength to a radiated wave to the magnetic field strength is constant. Antenna radiation resistance. This resistance does not dissipate power in the form of heat, as in electronic circuits. Instead, the power is dissipated as radiated electromagnetic impulse. Electromagnetic field. The electric and magnetic fields produced by the antenna are at the right angles of each other and both are perpendicular to the direction of propagation of the wave. Near field and far field. Antennas actually produce two sets of field, the near field and the far field. The near field describes the region directly around the antenna, while the electric and magnetic fields are distinct. The far field is the approximated 10 wavelengths from the antenna is the radio with the composite electric and magnetic field. Radio frequency identification. The near field is rarely used, but applications such as radio frequency identification or RFID and near field communication or INFC. Polarization. Polarization refers to the orientation of magnetic and electric field with respect to the Earth if polarized. Antennas that are horizontal to the Earth produce horizontal polarization, and antennas vertical to the Earth produce vertical polarization. Circular polarization. Some antennas produce circular polarization, in which the electric and magnetic fields rotate as they leave the antenna. Right-hand circular polarization RHCP and left-hand circular polarization or LHCP. There can be right-hand circular polarization and left-hand circular polarization. The type depends on the direction or rotation as the signal leaves the antenna. An electric field can be visualized as rotating as if the antenna were connected to a large fan blade. The electric field and the accompanying magnetic field rotate at the frequency of the transmitter. With one full rotation occurring in one cycle of the wave, Looking from the transmitter to the distant receiver, RHCP gives a clockwise rotation and the electric field, and LHCP gives counterclockwise rotation. Antenna reciprocity. The term antenna reciprocity means that the characteristics and performance of an antenna are the same whether the antenna are radiating or intercepting an electromagnetic signal. Note, an antenna can transmit and receive at the same time only if a device is such as the plexer is used to keep the transmitter energy out of the receiver. The plexer, a device used for this purpose. The basic antenna. An antenna can be a length of wire, metal rod, or a piece of tubing. Many different sizes and shapes are used. The length of the conductor is dependent on the frequency of operation. Common antenna types. All the most common antenna types of antenna used in communication industry are based on the basic dipole and most some modified form, the 1/2 wavelength dipole discussed in the last section. The dipole antenna. One of the most widely used antenna types is the half-wave dipole. This antenna is also formally known as Hertz antenna after Heinrich Hertz, who first demonstrated the existence of electromagnetic wave. Doublet. A dipole antenna is two pieces of wire, rod, or tubing that are 1/4 wavelength long at the operating resonant frequency. Radiation resistance. The transmission line is connected at the center. The dipole has an impedance of 73 ohm at its center with radiation resistance. Dipole length. An antenna is a frequency-sensitive device. End effect. It is a phenomenon caused by any support insulators used at all ends of the wire antenna and has effect of adding a capacitance to the end of each wire. Formula. L equals 4.92 times 0.95 over F, or 468 over F, where L is the length of half-wave dipole and F is the frequency. Antenna resonance. The antenna is 1/2 wavelength at only one frequency. It acts as a resonant circuit. Note, if a dipole is used a frequency different from its designed frequency, the SW rises and power is lost because the antenna impedance no longer matches the transmission line impedance. Antenna Q. The bandwidth of an antenna is determined by the frequency of operation and the Q of an antenna according to the familiar relationship. Antenna bandwidth. Although it is difficult to calculate the exact Q for the antenna, the higher the Q, the narrower the bandwidth. Lowering Q widens the bandwidth. In resonant circuit, high Q is usually desirable because it makes the circuit more desirable. Conical antennas. Another common way to increase bandwidth is to use version of the dipole antenna known as the conical antenna. Bow tie antenna. To use coaxial cable, which is usually desirable, some kind of impedance matching network is needed to transform the high center impedance to the 50 or 75 ohm characteristic of most coaxial cable. Note: most half-wave dipole antennas are mounted horizontally at low frequencies because the physical construction mounting the support are easier. Dipole polarization. Most half-wave dipole antennas are mounted horizontally to the earth. This makes the electric field horizontal to the earth. Therefore, the antenna is horizontally polarized. Radiation pattern and directivity. The radiation pattern of any antenna is the shape of electromagnetic energy radiated from or received by the antenna. Most antennas have directional characteristics that cause them to radiate or receive energy in a specific vertical antenna. A dipole is known as a directional antenna. For optimum transmission and reception, the antenna should be aligned both sides to the signal destination or source, beamwidth. The measure of antenna's directivity is beamwidth, the angle of the radiation pattern over which a transmitter energy is directed or received. Beamwidth is measured on antenna's radiation pattern. Antenna gain. Gain was previously defined as an output of an electric circuit or device divided by the input. Obviously, passive devices such as antennas cannot have gain in this sense. Formula is dB equals 10 log P out over Pn. Effected radiated power or ERF. The power radiated by an antenna would directly and therefore gain is called the effected radiated power or ERP. The ERP is calculated multiplying the transmitter power fed to the antenna P by the power gain A of the antenna. Formula of ERP is A sub P times P sub T. Isotropic radiator. An isotropic radiator is a theoretical point source of electromagnetic energy. The E and H fields radiate out in all directions from point source. At any given distance from the point source, the field forms a sphere. Folded dipole. A popular variation of the half-wave dipole is the folded dipole. Like the standard dipole, it is 1/2 wavelength long. However, it consists two parallel conductors connected at the ends with one side open at the center for connection to the transmission line. The Marconi or ground plane vertical antenna. 1/4 wavelength vertical antenna. Another widely used antenna is the 1/4 wavelength vertical antenna, also called Marconi antenna. It is similar in operation to a vertically mounted dipole antenna. However, it offers major advantages because it is 1/2 to the length of a dipole antenna. Radiation pattern. Most half-wave dipole antennas are mounted horizontally, but they can also be mounted vertically. The radiation pattern of a vertically polarized dipole antenna is still donut shaped, but the radiation pattern as seen from above the antenna is perfect circle. Omnidirectional antenna. Antennas which transmit an equal amount of energy in the horizontal direction are called omnidirectional antenna because of the donut shape. The vertical radiation is zero and the radiation at any angle from the horizontal is greatly diminished. Vertical radiation pattern. 1/2 of the pattern is below the surface of the Earth. This is called the vertical radiation pattern. Ground plane counterparts. Once a good electrical connection to the Earth has been made, the Earth becomes what is known as ground radials. These horizontal wires at the base of the antenna are referred to as radials. Counterparts. The greater the number of radials, the better the ground and the better the radiation. The entire ground plane collection of radials is often referred to as counterpoise. Note, if a good electrical connection or ground plane cannot be made to Earth, an artificial ground plane can be considered of several 1/4 wavelength wires laid horizontally on the ground or buried in the Earth. Loading coil. A series of inductor called a loading coil is connected in series with antenna coil. The loading brings the antenna back into resonance at the desired frequency. Top hat, sometimes referred to as top hat. This structure increases the capacitance to surrounding items, bringing antenna back into resonance. Obviously, such an arrangement is too top-heavy and inconvenient for portable and mobile antennas. Directivity. Directivity refers to the ability of an antenna to send or receive signals over a narrow horizontal directional range. Note: directional antennas provide great efficiency of power transmission because the transmitter power can be focused into a narrow beam directed toward the station of interest. Bidirectional antenna. The half-wave dipole antenna is directional in that no signal is radiated from or picked up from its ends. Such an antenna is referred to as bidirectional since it receives signals best in two directions. Unidirectional antenna. An antenna can be designed to as unidirectional. Unidirectional antennas send or receives signals in one direction only. Minor loop. The three smaller patterns of the loops going off in a different directions from the main larger pattern is called minor loops. Relationship between directivity and gain. The relationship between the gain and the directivity of an antenna is exposed in mathematical. The formula B equals 203 over 10 raised to n, where B is the beamwidth of antenna and n is the antenna power gain in decibels divided by 10. Antenna array. To create an antenna with directivity and gain, two or more antenna elements are combined to form an array. Two basic types of antenna arrays are used to achieve gain and directivity. Parasitic array. A parasitic array consists of a basic antenna connected to transmission line plus one or more additional conductors that are not connected to the transmission line. Parasitic elements. These extra conductors are referred to as parasitic elements and the antenna itself is referred to as driver. Reflector. The reflector, a parasitic element that is typically about 5% longer than the half-wave dipole driving element, is spaced from the driving element by a distance of 0.15 to 0.25. Director. Another kind of parasitic element is a director. A director is approximately 5% shorter than the half-wave dipole driven element and is mounted in front of the driven element. Yaji antenna. An antenna made up of driven element and one or more parasitic element is generally referred as Yaji antenna, after one of its inventors. The antenna elements are usually made of aluminum tubing and mounted on an aluminum cross member or boom. Driven array. The other major type of the directional antenna is a driven array, an antenna that has two or more driven elements. Collinear antenna. Collinear antenna usually consists of two or more half-wave dipoles mounted to end. The length of the transmission lines connecting to the various driven elements are carefully selected so that the energy reaching its antenna is in phase with other antennas. Broadside antenna. A broadside array is essentially a stock collinear antenna consisting of half-wave dipoles spaced from one another by 1/2 wavelength, or two or more elements can be combined. End-fire antennas. The end-fire array uses two half-wave dipoles spaced 1/2 wavelength apart. Both elements are driven by the transmission line. The antenna has a bidirectional radiation pattern but with a narrower beam width and lower gain. Log periodic antennas. A special type of driven array is the wide bandwidth log periodic antenna. The length of the driven element vary from long to short and related logarithmically. Impedance matching. One of the most critical matches of the antenna system is to ensure maximum power transfer from transmitter to the antenna. Note, when impedance mismatch occurs between antenna and transmission line, the problem might be corrected by adjusting the antenna's line to minimize the SWR or by inserting an impedance matching circuit or an antenna tuner between the transmitter and transmission line. Q sections. A Q sections or matching stub is a 1/4 wavelength coaxial or balanced transmission line of a specific impedance that is connected between a load and a source for purpose matching impedances. 1/4 wavelength transmission line can be used to make one impedance look like another according to the relationship. Balloon. Another commonly used impedance matching technique makes of a balloon, a type of transformer used to match impedances. Parallel winding in which two parallel wires are wound together as one round core provide maximum coupling between wires and core. Note, using an antenna tuner at a transmitter only tricks the transmitter into seeing a low SMR when in actually the SMR on the line between the tuner and antenna is still high. Antenna tuner. An antenna tuner is variable inductor, one or more variable capacitor, or a combination of these components connected various configurations. LT and Pi networks are all widely used. Transmatch circuit. One popular variation of antenna tuner is transmatch circuit, which uses a coil and three capacitors to tune the antenna for optimal SWR. Capacitors C2 and C3 are ganged together and tuned simultaneously. Radio wave propagation. Once a radio signal has been radiated by an antenna, it travels or propagates through space and ultimately reaches the receiving antenna. The energy level for the signal decreases rapidly with distance from the transmitting antenna. Optical characteristics of radio wave. Radio waves act very much as light waves do. Light waves can be reflected, refracted, and focused by other objects. Reflection. Light waves are reflected by a minor. Any conducting surface looks like a mirror to a radio wave. So, radio waves are reflected by any conducting surface they encounter along a propagation path. Refraction. Refraction is a bending of wave due to physical makeup of medium through which the waves passes. The speed of the radio wave, like the speed of light, is approximately 300 million meters per second in free space. Index of refraction. The degree of bending depends on index of refraction of a medium, obtained by dividing the speed of light in a vacuum and the speed of light wave in medium that causes the wave to be bent. Snell's law. The relationship between the angles and the incidences of refraction is given by a formula known as Snell's law. N1 is equal to sine of the angle 1 equals N2 over sine of the theta 2. N1 is the index of refraction of initial medium. N2 is index of refraction of medium into which wave passes, and theta 1 is the angle of incidence and theta 2 is the angle of refraction. Diffraction. Some signal usually gets through due to the phenomenon of diffraction, the bending of waves around the object. Diffraction is explained by what is known as Huygens principle. Huygens principle based on the assumption that all electromagnetic waves, light as well as radio waves, radiate spherical waves fronts from a source. Radio wave propagation space. Ground wave. Ground or surface waves leave an antenna and remain close to the earth. emitted by the antenna into the upper atmosphere, where they bend back to the Earth, ionosphere. This bending is caused by the refraction in a region of upper atmosphere known as ionosphere. D and E layer. The D and E layers are the farthest from the Sun, are weakly ionized. These exist only during daylight hours, during which they tend to absorb radio signal in the medium frequency range from 3000 kHz to 3 MHz. F layer. The F layer is subdivided into F1 and F2 layers. The F1 and F2 layers are the closest to the Sun, most highly ionized, and have the greatest effect on radio signals. The F layers exist both in day and night. Note: AM broadcasts are propagated primarily by ground waves during the day and by the sky waves. Skip distance. The distance from the transmitting antenna to the point on the Earth where first refracted signal strikes to the Earth to be reflected is referred to as the skip distances. Skip zone. If a receiver lies in the area between the place where the ground wave is fully attenuated and the point of first refraction to the Earth, no signal will be received. This area is called the skip zone. Space wave. The third method of the radio signal propagation is direct waves or space waves. A direct wave travels in a straight line directly from the transmitting antenna to the receiving antenna. Line of sight communication. Direct wave radio signals are often referred as line of sight communication. Direct or space waves are not refracted, nor do they follow the curvature of the Earth. Note: repeaters are widely used to increase the communication range for mobile and handheld radio units. The formula for computing the distance between a transmitting antenna and the horizon is D is equal to the square root of 2h, where h is the height of the transmitting signal and d is the distance from transmitter to horizon. Radio horizon. This is called the radio horizon. Repeater. A repeater is combination of receiver and a transmitter operating on the separate frequencies. Trunk repeater system. Although multiple repeaters can be used to ease overcrowding, they are often inadequate because communication activity is not equally distributed among them. This problem is solved by using trunk repeater system in which two or more repeaters are under the control of computer system that can transfer a user from an assigned but busy repeater to another available repeater. Communication satellite. The ultimate repeater of course, a communication satellite. Most communication satellites are located in geostationary orbit or 22,500 miles above the equator. Transponder. The receiver-transmitter combination within the satellite is known as a transponder. Most satellites have many transponders, so that multiple signals can be relayed, making possible worldwide communication at microwave frequencies. Calculating receiving power. A transmitted signal is at specific power level. The output power of transmitter can be accurately determined by the calculation or measurement. The power density at a given distance from an isotropic radiator is predicted by the formula PD is equal to PT over 4 pi d squared, where PD is the power density of signal, D is the distance from the point source, and PT is the total transformed power. Path attenuation. Another way to predict power is to estimate the total power attenuation over a transmission path. The attenuation in decibels is given by dB loss equals d 37 dB plus 20 log d, where f is the frequency of operation and d is the distance traveled. Common propagation problems. Fading. One of the primary effects of propagation is called fading. Fading is the variation in signal amplitude at the received caused by characteristics of the signal path and changes in it. Shadow fading. Fading is also caused by an object coming between the transmitter and receiver, known as shadow fading. This occurs if a vehicle containing a receiver moves in such a way that a large building for a mountain comes between it and a base station transceiver. Multipath interference. One of the sources of fading is the multipath interference. Rayleigh fading, sometimes called Rayleigh fading. This type of fading occurs when a transmitted signal takes multiple paths to the receiver because of reflections. Diversity system. Fading can also be minimized using the diversity system. A diversity system uses multiple transmitter receivers or antennas to mitigate the problems caused by the multipath signal. Spatial diversity. Another more widely used form of diversity is called spatial diversity. It uses two receiver antenna spaced as far apart as possible to receive the signal. Receive signal strength indicators or RSSI. In cell phone system, these circuits are called receive signal strength indicators. They determine the signal with the greatest strength and switch the signal to reminder of the receiving circuits. Thank you for watching.